Hey there, Ravens. Welcome to Atomic Theory Part 6. Today we're going to talk about electromagnetic spectrum. Okay, so the electromagnetic spectrum includes all forms of radiation. In other words, energy that travels in the form of waves. And this is a cool diagram. We looked at it in class. If you want to study it a little bit more, it's here. You have wavelength in meters. You have some objects representing the size of the wavelength, just to give you an idea. And then the common names of the different waves, sources of them, frequency is on here as well as the energy of one photon. Okay, and a photon is a very small packet of energy that travels in the form of waves. So how energized it is. Okay, and as you move over and get into the smaller ones, that's where we get our radioactive rays, our gamma rays, alpha rays, and beta rays are on here as well. They're not on here, but they occur more in this range over here. Okay? All right, here is a good movie on the electromagnetic spectrum.
The electromagnetic spectrum, an immense scale we use to measure the wavelengths of all kinds of radiation. At one end are radio waves with the longest wavelengths. At the other end are gamma rays with the shortest. In between are the other bands, including visible light, which is such a tiny fraction of the whole, it's difficult to imagine. How small is the visible spectrum? If you had a reel of movie film representing the entire electromagnetic spectrum, stretching 2,500 miles from California to Alaska, the section containing the visible spectrum would fall somewhere in the middle, near the University of Washington.
This frame is the whole visible spectrum. It is one frame in over 2,000 miles of tape, and it's everything that the human eye can see. The importance of this frame is that stars emit almost all of their light in this part of the spectrum.
And even though the light is visible, it still contains hidden tools. The secrets are in the spectrum itself. The visible light in this lamp comes from hydrogen gas excited by electricity to form a glowing plasma, similar to what happens in a nebula. By viewing the lamp through a diffraction grating, we can split the light up into 3 narrow lines on the spectrum, a virtual fingerprint of light, unique to hydrogen alone.
So in the spectrum, you see 3 features. One is red, one is a light blue, and the other is a deep blue. This pattern of wavelengths is absolutely unique to hydrogen, and there's no way to confuse hydrogen in the spectrum with any other element.
Okay, and so where we want to get from this is that visible light occurs in a continuous spectrum, okay, where the colors blend one into the other. Emission spectra is a unique test that is able to be done because light from an element that's passing through a spectroscope appears as a series of bright lines. Okay, so over here we're energizing the element. You shine that light through the prism of the spectroscope and you get a very unique set of bands of lights. This is so unique to elements that we are able to use it to identify stars or galaxies. And I believe you guys read an article about the space rover on Mars. Well, Mars' space rover has a spectroscope on it, so it is able to take up samples of soil and energize it, vaporize it basically, put it through the energizing, making it, and then test through the spectroscope to see what are the elements and compounds that are found on Mars. So Pretty cool stuff. Emission spectra, able to identify elements with it unique, like a fingerprint. Okay, and I think this is our last slide. It is. We're all done for the day. I'll see you next time. So long.